begin. Before the turn of the century, radiations were discovered that weren't known about. And they call these, guess what? X-rays. And these X-rays turned out to be simply a high-frequency light. Remember we talked about exciting atoms? You got an atom with the electrons going around and around, and an electron or light or something hits, makes an electron go up, come back down, boom, off goes the energy in the form of light. The same thing happens when you excite the innermost electrons. If you excite those, it takes a lot more energy. And you knock an electron way up and it comes way back down, boom. That light photon that emerges is beyond the range of seeing. It's even beyond the ultraviolet. And that's what X-rays turned out to be. Simply high-frequency light from the orbital electrons jumping orbits that correspond to great energies. But after that, it was found that there were radiations coming from different minerals that did not have to do with the electron orbiting around the nucleus. They had to do with the nucleus itself. And the radiations that were emitted, to make a long story short, were three different types. Now, you might think they'd call them maybe A, B, C, right? But these are physicers, gang. We didn't call them A, B, C. You know what we called them? Alpha, beta, gamma. That's A, B, C in Greek, yeah? So alpha, beta, gamma rays. And it turns out that those radiations, you can find out there's three different types of radiation by simply getting a lead block, boring a hole in it down to about the center, and then putting in some radioactive substances. These are heavy minerals. And it turns out these radiations will be emitted in all directions, but the ones coming out here will comprise a beam. And then in that beam, if you put a magnet, it turns out that in that magnetic field, the beams will separate. Some will. Some will just keep right on going. And some will bend this way, and some will bend that way. And if you had a piece of photographic film out here, you could catch splotches here, here, and here. Three distinct splotches, which would indicate there are three different kinds of rays coming out. We call one the alpha ray, we call the other the beta ray, and we call the one that's undeflected the gamma ray. So alpha rays are charged one way, and beta rays are charged the opposite. Opposite charged rays. So these rays were comprised of particles with electric charges. To make a long story short, the alpha particle turned out to be, the alpha radiation turned out to be the nucleus, the nuclei of helium atoms. And it turns out that the beta particles were electrons. Just plain old electrons like that would flow in an electrical circuit. And it turns out that the gamma, alpha, beta, gamma, is just your E and M radiation. Doesn't have any charge, just like light ray doesn't have any charge. It's just pure energy of electromagnetic fields, okay? And your beta particles, just electrons, and your alpha, helium nuclei. Now those helium nuclei, an alpha particle and a beta particle brought to rest will make up what's called a helium atom. Because this is the nucleus, this is the orbiting electron, and so the next time you see a kid walking by with a balloon filled with helium, tell the kid's mother, hey kid, you know what's in that balloon? And just tell the mother, that's radioactive debris from uranium and radium and dangerous things like that. True or false? That's true. That's true. But these particles now have lost their energy. If you walk by an old historic site and you see an old cannon, and you see some of these cannonballs all sitting, all piled up, do you get scared when you walk by those cannonballs? You don't get scared when you walk by those cannonballs. They have no more energy. Not the energy they had when they were projectiles in some war or something. So just as those cannonballs are not dangerous anymore, the alpha particles that in the beta particles that make up helium gas in a balloon is not dangerous. They've lost their energy. This piece of chalk isn't dangerous, but if I put this piece of chalk in a shotgun and fire it at you, then it is. And that's the difference between the particles that are ejected from the nucleus. They come at very, very high speeds. High speeds, a lot of energy. They can tear into you, and then maybe that's not so good. But once stopped, they're completely harmless. Any questions at this point? Let's continue. Begs the question, why is it that atoms are radioactive anyway? And it turns out all the atoms beyond atomic number 83, they're all radioactive, which is to say they're unstable. They decay. What's going on? Remember we talked about the fundamental rule of electricity? And that fundamental rule was that like charges repel and unlike charges attract? Let's consider a proton here. And now another proton right next to it. According to what we learned about electricity and magnetism, what will happen here? Beginning with an R and with repel. Try it. They're going to repel. A lot or a little? And so begin with an L. A lot. There's going to be a huge force of repulsion. But you know what? They don't do that. Not quite. These would. And you won't find that in nature. You won't find in nature two protons stuck together like that are stable. It turns out that the force of repulsion is like this. But there's another force inside just about stronger at this level. And that force is called the strong interaction. And the strong interaction is holding these things together, so the whole net force is about zero. But not quite. It's still unstable. So what you do is you put another particle in here with no charge, and that's a neutron. Are you on to protons and neutrons? Both of which are made up of even fundamental, more fundamental particles called quarks. But these neutrons don't repel. See, there's no charge. So the neutron only holds. So it binds, it holds this to that. That neutron plays the role of like a nuclear cement. And if you have something like this, two protons with a couple of neutrons, the nuclear force is awesome compared to any repelling electric force. And that particle is stable. Nuclear force wins, or the nuclear interaction wins. See, the nuclear interaction, as you read in the textbook, is a very, very short-range force. Over long distances, like a couple of diameters away, it's trivial, but very, very close, humongous force. But the electrical force, that peters off as the inverse square of distance. I mean, if you get twice as far away. In fact, I wonder if you guys can answer this. With the electrical force, if you got a couple of particles twice as far away, would the electrical force be weaker? I think people out in the street could answer that. But people out in the street couldn't say how much weaker. See if you're sitting next to someone who knows how much weaker would the electric force of repulsion be with particles twice as far apart. Check. What's the answer, gang? How many say a fourth? Show of hands. Hey, we're learning this stuff. That's a typical final exam question. Now that one, duck soup, yeah? I mean, you've learned that. Inverse square law. Twice as far away, 1/4 the effect, okay? So as these things get further and further away, the electrical force kind of peters down. But the strong interaction really, really peters down. And that means that you can't really have a very big atomic nucleus. And here's why. Let's suppose you have a big nucleus that's this big. You've got a proton over here and protons over here. They're so far apart. The nuclear interaction between these two is almost trivial. But between these two, the electric repulsion is not trivial. And so what happens, very, very large nucleus, just by virtue of the spreading apart, are unstable nuclei. And that's beyond 83, atomic number 83. Every atomic nucleus above atomic number 83 is unstable. And in that environment, you have then the ejection of alpha, beta, and gamma particles. So it's almost simple geometry. Right now, this particle we call an alpha particle. This is a helium nucleus. And I'll write that helium nucleus like this. And I'll put a 2 down here and a 4 here. And this nomenclature I hope you're familiar with. This is simply the atomic number. It tells you it's at atomic number 2 in the periodic table of substances, yeah? It's got two positive charges. And the 4 refers to the atomic mass unit. And that's the number of nucleons altogether. I call these, by the way, nucleons. I can call you a people, a person. But a person can be a male or female. Nucleon can be a proton or a neutron. See what I'm saying? But there's 4 nucleons altogether. So it has a mass of 4 and atomic number 2. So that would be the configuration. If I put another proton in there, then it would now be, does anyone know? It would be the element lithium, because now it would have 3, and up here would be 5. And any nucleus that has 3 protons, by definition, and by chemical properties, will be that which we call lithium. And you guys know about that. The number of protons in the nucleus dictate what the nucleus is. Okay. Like, what is it, 82 for lead. Anything with 82 protons, honey, that's lead. Anything with 92 protons, what's that? Anything with 92 protons. What kind of age do we live in, gang? Me with a U. Uranium, right? It's uranium. And we can have something like this. The most common form of uranium is uranium-238. We say this is the isotope of uranium, the isotope 238. You're on to what isotope means. You can have atoms with a variety of neutrons. This atom here has 2 neutrons. It would still be the same element if it had 3 neutrons, but now it would be a different isotope. Isotope's another word for kind of at the nuclear level. Okay? So this is the isotope 238. Notice that there are many, many, many more neutrons than there are protons. If you subtract 92 from 238, I think you get, what is it, 146? 146 neutrons, but 92 protons. It turns out as your nucleus gets bigger and bigger and these things get further and further apart, you need more nuclear cement. You get the elements up to about 20. Look in the periodic table and you'll see the atomic mass is always about twice the atomic number. See? When you get up at about 20, you get equal numbers, roughly, of neutrons and protons. But above 20, you need more nuclear cement, and then you find your atoms have more neutrons. When we talk about, oh, by the way, we have a little model here of the helium atom. It's brought in by Paul Casey. And what this is, we have the 2 protons, 2 neutrons for the nucleus, and we have orbiting 2 electrons, which make up a helium atom. Little model, the planetary model of the helium atom. Rip these 2 things away, and what do we call that helium nucleus?
Alpha.
Alpha what? Particle. Cull. Good. Cull. You get the cull. You get the cull? All right. Particle. All right. Good. Hey, when we measure how radioactive something is, and radioactive just means that things are unstable, they're busting apart, so it's emitting these particles. The measure of radioactivity is popularly called half-life, radioactive half-life, and that's an easy concept to get. How hot something is. Hot. Oh, you know why we say radioactive things are hot? Why do we say radioactive things are hot? Watch out for that uranium. That's hot. Is it literally hot, temperature-wise? What do you suppose? Answer end with a P. Not P-E, just P. Try it. Yep, it is hot. Why do you suppose it's hot? Why would a piece of uranium be hotter than a piece of rock in the same environment? A rock meaning a rock with no uranium or radioactive minerals. Well, why do you suppose?
Releasing energy. Because
Check your neighbor in this one. This is some you guys have enough physics to do this? What does it mean to say something's hot? Hot temperature-wise.
Well, they're emitting alpha and beta particles, and those are going at high speed and hitting the other atoms and making them move faster.
Yeah, just to say something's hot means things are moving faster, honey. Little particles moving fast. Guess why they're moving faster? They've been kicked around. What's kicking them around? How about some alpha particles start hitting you, honey? You'll be hot too. They're gonna just kick around a little bit. That's all. It's that simple. So it turns out things would be. Why do you suppose we're getting all these volcanoes over there in the Big Island? Where's that heat coming from? Oh, that's the Earth, honey. The Earth's natural heat. Well, where did the Earth get the natural heat? Come on, where's it come from? Where are volcanoes coming from? What's the source of energy making a volcano do its thing? Begin with R. Radioactivity, honey. Radioactivity. And down there is a lot or a little? Yeah, a lot of people think radioactivity is something new, huh? New. Radioactivity been around before the world got here. This whole world is hot because of radioactive decay. Next time you bathe in a nice hot spring, say, hey, this is nature's hot water, honey. Guess where that nature's hot water gets its heat? Radioactive decay. Down in the ground, see? And so that, hot. That's where the heat comes from. Natural? Yeah, it's natural. Been around a long time. So we talk about half-life in terms of how long does it take for half of the radiation rate to get to half. How long does it take for half of the atoms to decay? See, if you start off with something like some pure radioactive substance, sometime later that substance will all convert to something else. Like all the uranium that exists in the world today will one day be lead. lead. Whether the world survives or not, will all be lead. Now, how long does it take for half that uranium to decay? It turns out a long time. It turns out 4.5 billion years. Yeah. And you know, when I used to prospect for uranium, I used to find uranium, you know? And every time I'd find uranium inside that rock, guess what also was there?
Lead.
Lead. And guess how much lead compared to how much uranium? About same. Which means that what? The age of that rock is about what? 4.5 billion years. That's the age of the Earth. So 4.5 billion years is the radioactive half-life for the isotope uranium-238. That means in 4.5 billion years, all the 238 atoms around, half of them on the average will have decayed to something else. Now that's a long half-life. A shorter half-life is like radium. Radium, I think, is 1,620 years, something like that. And radioactive carbon-14, that's 5,730 years. And little neutrons, it turns out a neutron by itself is radioactive, will decay. And that'll decay in about 12 minutes. Half-life about 12 minutes. And then a little mu mesons that are 2/millionths of a second, half of them will decay. So there's a whole range of radioactive half-lives. And here's the old story. Let's suppose you have a gram of radioactive substance, and it has a half-life of 1 day. Something used maybe in medical research, yeah? 1 day. How much of that gram will be left at the end of 1 day? And still be the kind of substance it is. Begins with a H. Very good. How much will be left at the end of 2 days?
1/4.
Quarter.
Right. Don't be wimpish. Come on. Get it out. You are university level, right? 1/4, honey. All right. Now, what would the wimps say? 0. They say 0. Say, well, you lose a half one day, you lose a half the next day, it'll be gone. What do we university types think about that? Needs a little more careful scrutiny, right? Because you could have started off with a half to begin with, right? Okay. It's going to keep going half. It's like the old bit about, do you ever talk about this thing? We're going to jump to the wall, and every time I take a jump, I get halfway to the wall. How many jumps before I hit the wall? And what's the answer?
Never.
You guys heard of that before. You'll never hit the wall. If every time you jump, you get halfway. Let's suppose I want to go from here to here. Whoop, it's a half. Then 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 I never get to the wall. So in a similar sense, with radioactive decay, you never get to a point where there's no more atoms left. In a practical sense, sure you will. But when you're talking about radioactive decay, it's always nice to work with large populations. Hence, half-life is more meaningful in that sense than going for the life of the whole thing. You might have one that, let's suppose you go, and there's one left. And 20 years later, now, does it make sense to say the lifetime of that material is 20 years? No. Take half of that. That time, you got enough large numbers in there that your half-life, your value can have more meaning. Can be more close to what is there. Transmutation is the word given to atoms when they change from one form to another. The alchemists of old used to believe that you could transmute the atoms. You could start maybe with lead and go to gold, or you could start with mercury and turn it to silver and things like that. And it turns out they could never do that. And the reason they could never do that was because they were using chemical means. Gang, when we talk about this nuclear stuff, we're talking way down beneath where the electrons are, way down in the nucleus itself. And in that nucleus, the reactions there have nothing to do with what's going on outside, like heat and temperature and pressure and things like that. Okay, the nucleus is pretty well insulated from all that. And so the processes that happen way down deep in the nucleus, in fact, the alchemists didn't know it, but radioactive decay is happening all around you. But they had no way of detecting it, and if they did have a way of detecting it, they wouldn't have understood it because they didn't have the nuclear model. But I have a model for hanging your ideas upon. That model was not developed then. So radioactive decay, the idea that atoms change from one atom to another, is happening all the time. So all the uranium transmutes to other atoms in step-like fashion until they become lead. Let's go through some nuclear reactions. This is kind of fun to see how these transmutations occur. A natural transmutation is uranium emitting an alpha particle. We write like this. We start with uranium, an element of uranium, and an alpha particle is emitted. And an alpha particle is simply a helium nucleus. Now this is a numbers game. What does the uranium turn into? Well, maybe we don't know, but we know one thing, that the number of charges you began with will equal the number of charges you end up with. That's called the conservation of charge. You can never give a reaction where the net charge before and the net charge after is different. Charge is conserved. So you start with 92 positive charges, you're going to end up afterwards with 92 positive charges, but 2 of them are here. Guess where the others are? They're in this other element, and that must be 90. Let me show you how that works. 90 plus 2 equals? 92. Yum, yum, okay? All right. Now there's another thing called the conservation of nucleons. Here's something. When an atom decays, the number of nucleons after is the same as the number of nucleons before. They might be rearranged, but the same number. Now we have 238, but we got 4 there. So how many are going to be left in this other particle? And that's going to be 234. And then you can look up at the periodic table at the inside cover of your book and to find out what element has atomic number 90. And is that not thorium, gang? See right in the periodic table, whip them, thorium. And that's going to be TH. Now thorium itself is radioactive. Thorium decays as well. If it decays into an alpha particle, you check with your neighbor what's going to be the atomic number of what's left over. Is it 88? How do you know it's 88? Because 88 and 2, honey, is 90. Yay, huh? Same charge before and after, right? What's going to be the mass of that particle?
230.
How do you know it's 230? Because 230 and 4 is 234, okay? And that element's going to be what? Radium. Ever heard of radium, gang?
Radium.
All right, radium, all right. Okay. Let's suppose it does not emit an alpha particle. It can emit a beta particle. If it emits a beta particle. Beta particle, beta particle, beta. What's a beta particle? Electron. Now we have to make the symbol for electron. E for electron, get it? What's the atomic number of an electron?
-1.
Atomic number?
-1.
What is atomic number anyway? Charge, right? What's the charge of an electron? -1. What's the mass of an electron?
0.
Well, it's closer to 0 than it is to 1. If 1 is the mass of a proton or a neutron, and this has got like about 2,000th the mass, that's closer to 0 than to 1. So we round off atomic mass number anyway. It's 0. Now, what does the thorium become? Well, what do we got over here for an atomic number?
91.
Do you see it's 91? And what's the mass going to be?
89.
Now, what has 91?
Potassium.
Is it going to be 91, gang?
Yeah.
Let's check. 91 minus 1 equals 90. It's 91. That's interesting. Some people think that radioactive decay, you start with uranium and work down, 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 down the periodic table, approaching hydrogen. Not true. When beta particles are emitted, you climb up the table, gang. You see that? What happens in that nucleus? You got all these particles in that nucleus. I'm not going to draw them all, but we've got 90 of them, right? And take away 90 from 234, the rest are neutrons. So you got a lot of neutrons. What happens is this. One of these neutrons, you can think of that neutron as being like this. Now it's not, but you can think of it as being a plus and a minus together, which is what? Neutral. And what happens if a negative flies out? What's this become? A plus. And that's what happens. That's what happens. One of these neutrons emits a beta particle, emits an electron, and becomes a proton. And there's the extra proton. So you get the same number of nucleons. It's just that one of the neutral ones turned into a positive one. See that? So you're decaying up the table. And that element is what? 91. Protactinium, Pa. Not common, huh? These are natural transmutations. There are artificial transmutations. Transmutations that are induced. And one of the first that we have recorded is that which a fellow by the name of Ernest Rutherford made in, I think, 1919. And all Rutherford did was what did he do? He had some nitrogen gas in a container, and he put inside a piece of uranium, or was it radium, I don't know, that was emitting alpha particles. And then he found the nitrogen gas later on contained trace amounts of oxygen. And what was happening was the alpha particles were coming out, hitting the nitrogen gas, and boom, making the gas turn from one element to another. And that's where there was a nuclear interaction. And let me draw that. Let me write that interaction on the board. You had nitrogen, which is atomic number 7, got as many neutrons. It's not nitrogen 14. You're breathing that all the time, gang. It doesn't do anything for you. It takes up space, gives you the pressure in your lungs, yeah? But when an alpha particle, boom, bams into that, the following was shown to be the case. I think they took photographs with cloud chambers, and out of millions, they got millions of, I think 250,000 photographs. They found 6 reactions, which were this sort of thing here. It turns out this knocked a proton loose from the nitrogen. And when it knocked a proton loose, what's left over had, what do we got here, gang? 7, 8, 9. 1, 8. Whew! 8 is what? Biology types, chemist types, physics types? That's oxygen. What isotope of oxygen? Most oxygen is 16, yeah? But this isotope is what?
17.
If we put a 16 here, 16, 1, and 17, 14, 18, it's got to be isotope 17. And that kind of made some history. So the scientists succeeded in deliberately changing one element from one kind to another. Artificial transmutation.
That only occurs with nitrogen?
That occurs with this is the historic one. Now you do it with all kinds of things. Every time you slam particles down the end of an accelerator, you cause atomic nuclear transmutation. It's routine today. It's just that this historically was the first one that people were able to observe. That's artificial transmutation. Slam nuclei into others, and you rearrange them. That rearrangement process is called transmutation. Paul?
So what you're saying is today we can change lead to gold?
Yes, we can change lead to gold.
Would it stay?
And the cost of doing that will not be economical.
But
yeah.
Would the stuff stay that way, or would it be?
Oh yeah,
unstable?
yeah. Let it go. Yeah. Any other questions?
He said they took some pictures. How did they do that?
Photographs, cloud chamber photographs. I won't take the time to talk about cloud chamber photographs, but did you ever look up in the sky sometimes and you can see where an airplane's been? You see the trail going through? What those are is ice crystals. And the airplane has interacted with the air up there, a lot of H2O emitted by the exhaust, and you can actually see the track where the airplane's gone. Even if it's so high that the airplane can't be seen, you can see the track. A similar thing happens when particles go through a region that's just a gas, that's just about saturated, that's just going to turn into little droplets, and boom, the little particle comes by, knocks these things, and they do turn into droplets, and you can actually see the trail of these things. These can be seen with a naked eye, little cloud chamber tracks. If you go to a science museum sometime, you can actually see these things going on. You can look in this chamber, put a piece of radioactive material, and you see all the lines going out. You can see these are what? You see the little tracks of particles that are too small to be seen by the eye. The tracks can be seen, all the particles can't. They're too small, of course. But that's one way of doing it. Carbon dating. Transmutation happens in the atmosphere all the time. Here's a common reaction that happens in our atmosphere. First of all, the Earth is being bombarded all the time with high-energy particles. It's cosmic radiation. Radiations are the particles going through you all the time, splattering into the atmosphere of the Earth, all of the Earth. And a lot of these interactions eject neutrons. Neutrons are flying all around. When these neutrons hit the atoms of the air, we get kind of an interesting reaction. Here's nitrogen again. It's easy for neutrons to slam into the nitrogen nucleus. Very easy. It's easy for neutrons to slam into anything because the neutrons have no charge. See, it's hard to get two charged particles to slam together. Very, very difficult. Very, very rare. But it's very, very common for a neutron to splatter right into the nucleus of an atom because there's no repelling force. So there's no electrical interaction. So neutrons slam right in. Now, what's the neutron's atomic number? What's its charge? 0. What's its mass? 1. Those two things slam. And when they slam, boom, again, a proton pops out and leaves what? Well, whatever it leaves, it's got to be, what's it going to be over here again? 6. And what's the number's going to be? 14. Do you see it's 14? Hey, this is not twice this. This is twice and then some. This atom here has extra neutrons. It turns out that atom is unstable. That atom is carbon-14. Most of the carbon in your environment is carbon-12. But some of the carbon in your environment is carbon-14. And that carbon is radioactive. And that carbon emits a beta particle. Could you tell me what is left? Some people can, some people can't. Most of you, of course, begins with a C. The shorter version of C. Check your neighbor. What are the numbers going to be? And what's the number going to be over here? 7? Is it 7? If it's 7, does it check? 7 minus 1 is 6. What's 7? Nitrogen. What do we got for up here? What goes around comes around. Nature is cyclic, gang. You started off with nitrogen, whip, boom, you end up with nitrogen. But not right away. Not right away. The half-life of that reaction is 5,730 years. T, the radioactive half-life, is 5,730 years for carbon-14 to decay back into nitrogen. That means this. Everyone take a breath. Well, you don't have to. It's all right. Come on, here we go. You know what you breathed in? Some CO2. Now, you think all that CO2 was C12, right? Begin with a W. Wrong. Some carbon-12. So as soon as you take the breath, you blow it right back out again, right? But it all didn't come back out. What comes out is not the same thing that went in. Why chlorides? Some of it goes in and it stays. And when it stays part of you. But it's radioactive, ready to fire at any moment. Okay? And for every carbon-14 you bring in, it take on the average 5,730 years for them to fire off again. Okay? The half-life's that long. But gang, guess who's radioactive? Me or you? Or all of us? All of us? All of us, gang, we're radioactive. Okay? Because we're composed of carbon. Okay? And a lot of that carbon is carbon-14. And it's radioactive. Now what happens when the bad day comes and all of a sudden you check out and you're no longer breathing in anymore? Do you become less radioactive or more radioactive?
Yes, because you're under the ground.
Ooh, you don't be seeing that. You don't be seeing that. So long as you keep breathing in, you're breathing radioactive materials in, right? They become part of you. But when they become part of you, don't they decay? Once a carbon-14 decays, is it radioactive anymore? No, now it's nitrogen. nice and stable nitrogen. So what happens is when you die, you become less and less radioactive. You're the most radioactive right now. Now, if you stop breathing, you become less and less radioactive. How? And stop eating. Every time you eat a tomato, there's carbon in it, right? Carbon in everything you eat. Is there any food you eat that doesn't have carbon in it? Okay. And some of this carbon's carbon-14. So when you die, or when anything that breathes in, that takes in carbon-14 dies, it becomes less and less radioactive, hence radioactive dating, carbon dating. You've heard of that before. You want to know how old an old tree is or something like that. You should take a little bit out. That being the half-life, let me give you an example. You're with your friends, you're up country, you go into an old cave, and you say, hey, you know what, I think there was people in this cave long ago. And you dig down, you find evidence of an old campfire. And down in that campfire, you find an old axe. Maybe it's a caveman's axe or something, yeah? And that's the axe handle and everything. What you do is you take that axe handle, you come here to the university, go to the chemistry department, but first just take a little teeny sliver. They might want to hog the whole thing for themselves, right? It's your artifact, right? Take just a littlest, tiniest bit of flake of wood off there, okay? Take that wood flake off. go to the chemistry department, but before you go in the door, take your jackknife and take a little flake of wood off a tree that's living. Now you got 2 splinters of wood, yeah? One's the old, one's the light, yeah? Bring that to the chemistry department. Chemistry type? Yeah, chemistry type opens the door. Can you do something for me? Can you get the carbon out of these things? Yeah. When can you do it? Come back tomorrow. You come back tomorrow. Oh, and would you measure them out, by the way, so I get the same mass in each? You come back the next day. You get 2 envelopes. One says old, one says new. You're telling the guy what's going on, yeah? And you get the old and the new. Now they're both carbon. Huh? Look like, open it up, look like soot. Say, oh, chemist type, can I borrow a Geiger counter? Yeah, right over there. You get the Geiger counter. And you know what a Geiger counter is? Radiation detector. And you put the carbon under the radiation detector, okay? You put the new one in there, the new one, from the little twig that you put that under there. Click, 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 click. Maybe 20 counts per minute. Make believe. 20 counts per minute. Now, you take that away. Now you take the old one, put it underneath that. Click, 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 click. 10 counts per minute. Ooh. How old was the axe handle? Check your neighbor. How many be saying, oh, I think it's something like more than 5,000 years old? Show of hands. Yay, because it's a half-life. What if you put it under there and it went click, 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 5 counts per minute? And the new stuff is 20. Ooh. Then how old is the axe handle gang?
11,000.
11,000 something.
11,460.
Twice that? Yay. It'd be twice as old as the half-life. You got it? All right. How do they determine those numbers? Some guy was really, really patient and put some carbon in and kept waiting and waiting and waiting. And when it got down to halfway, he just sort of looked at the calendar and saw how many years went by. Not really. I'm joking. I'm joking. But how it turns out the radioactive decay rate and the half-life are related. If something has a very, very high rate of radiation, then its half-life is going to be greater. And a simple computation does that. Very, very short half-life, high rate. Long half-life, low rate. Let's suppose I have 2 substances, a gram of each. And 1 gram goes like that in the Geiger counter. The other one goes tit, 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 tit. Guess which one lasts for a longer time? Check your neighbor. Oh, tit, 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 tit. Check. Which one got the shortest half-life? Let's hear it. You guys can't do that? The shorter half-life, okay? It's not going to last, but it's running out. It's running down. See you guys on Wednesday. Wednesday we talk about fission and fusion.